This is lab number 5, Choose Your Own Adventure. We will be going over the falling Slinky. The purpose of this lab is to explore the interesting motion of a falling stretched Slinky in freefall, using both computational and experimental models to compare them and to understand the different forces that come into play. We will go over the physics concepts, computational setup, and analysis. So some of the physics concepts we will go over is basically, it relies on Newton's second law, like we've done for the previous labs, which states that the change in motion, or the acceleration of an object, is directly proportional to the force applied, or F net is equal to mass times acceleration. Over here, on our free body diagram, we have two different components into play, the top of our Slinky and the bottom of our Slinky. They experience different things. So during the first part, the top of the Slinky has drag force and the force of gravity that's pulling it down. However, the bottom of the Slinky has something called force of the spring, which is the Slinky itself, or force of tension. The force of spring is negative K times delta S times L naught, and the force of gravity is, of course, negative mg. And so we will calculate the velocities and the position of the Slinky as it falls into free fall using the velocity and position update formula to update them. And the results of our findings. Interestingly enough, the bottom of the Slinky does not fall down until the top of the Slinky reaches the bottom. As you can see here, these are two different clips at two different times, and the bottom has stayed stagnant while the top has gone down. The procedure and experiment. For this procedure, we have our system, which is our Slinky, our surroundings with our earth and air resistance, and our initial conditions, which is the mass of our Slinky is 0.281 kilograms, and our position is 0.489 meters from the ground. This is because we put y equals 0 to the ground, and it was released from rest, which means there was no initial velocity. So first, we're going to upload our video to Tracker and track our object's position over time, and then create a computational model based on our Tracker video, basically modeling what would happen to our Slinky, and compare these graphs and draw conclusions on possible sources of error. So here's our Tracker video here, at least a picture from it. And as you can see that we have tracked the bottom of the Slinky, not the top of it. And we can see that the bottom stays stationary. And then in the position when the top reaches the bottom of the Slinky, they fall down. And air resistance is giving it constant velocity downward here. As you can see that the position time graph as it goes downward is pretty linear. And this is because of equal forces. So in setting up our computational model, so to set it up, we have our different constants. As you can see here, we have our little graph, and our position at the start is 0.489 meters from the ground. Our velocity is 0 because it's released from rest, and gravity is 9.8, and we put our proportionality constant, or the air resistance, to 1, and we have t and delta t. Our while loops for a computational model. When the bottom of the Slinky is stationary, this is when the top of it is going downward, but it has not yet hit it yet. And this means that there's force of tension pushing it upward, pulling it upward, and force of gravity pulling it downward. But when we add those two things together, it equals to 0. And as we have a F net is equal to 0, our velocity doesn't change, and our position also doesn't change. But after, when the fall tops and collides with the bottom, now there's no force of tension, and it's just the force of gravity and the force of the air resistance, which when we add those together, it's going to give us going to add to our velocity and add to our position. Data analysis. So compared to these two graphs that we created here, they're pretty much the same. There's a little more discrepancy in our tracker model just because when we're tracking it. And we'll go over this in our possible errors. But basically, as you can see here, until around the time of 6 seconds, there is a straight line because the bottom is stationary, and then it will go downward as the whole entire thing falls to the ground. So possible sources of error, like we talked about before, is human error in tracking. And there's also other external factors that we're not considering since it's an open system, and our tracking software is not 100% accurate. So now going some what ifs and what does it mean? What does it mean to have air resistance here? So air resistance is a force that acts upward or against gravity, and it's really dependent on the velocity of the Slinky. This means that they would have no effect if the Slinky was stationary, such as the bottom. As you can see, we did not have air resistance in our equation for our forces because there's no velocity, so there's no air resistance, and then applies and works against the force of gravity once the entire thing is pulled to the ground. If there was no drag force, then the Slinky would fall down faster since there's no force pushing it upward. What if the Slinky was initially thrown downward? If it was a stretched Slinky and the top of it was thrown downward, then the top of the Slinky would have an initial velocity and reach to the bottom of the Slinky with more than just the acceleration of gravity, which means it would take less time. The bottom of the Slinky is ineffective until the top reaches the bottom, but this would mean that the top would reach the bottom faster, and it would decrease the time for the Slinky to finally reach the ground.